Hi, my name is Mike Peters. This is my class project, which is on active learning for text classification. As background, supervised machine learning is a common tool used in document classification problems in the IR space. Supervised machine learning requires a lot of labeled examples, which it takes a lot of time and is very expensive to collect. There's a clear motivation to try to find a way to train good models using fewer labeled examples. So is there a way? Yes, that way is using something called active learning. So active learning is the process of using some selection criteria to choose high-value examples from the data to be labeled by some expert in order to help the underlying model to learn the topic. There are two main types of active learning, selective sampling and pool-based active learning. Selective sampling is where each document is analyzed by the active learner when it comes into the system, and a decision is made about whether to collect the label or not. Pool-based active learning will operate on a pool of possible examples, and it'll select some number of those examples from the pool to show to an expert to collect a label from. There's also a lot of different strategies for how to choose documents in active learning. Some of the different methods include uncertainty sampling, version space reduction, query by committee, and expected error reduction. For this experiment, we're going to be looking exclusively at uncertainty sampling using a pool-based active learning scenario. So for this experiment, I chose to use the Reuters RCV1 dataset for the experiment. That dataset contains over 800,000 labeled documents, all of which have been classified into over 100 different topics. So for this experiment, we'll be looking at 8 distinct topics from that data set with varying numbers of positive examples, so you can see those here. For the experiment, we're going to utilize the LYRL 2004 split of RCV1, which holds 23,000 or so documents for training and puts the rest into a test set. We're then going to split that training data into 10 folds. To start, we'll train a two-class classifier that classifies about or not about for a given topic, and train it on the first fold of the training data to represent model initialization, so it starts with some knowledge of the topic. We're then going to apply our active learning methods and iteratively choose 50 examples from each of the remaining folds. The folds represent the pool for pool-based active learning, and out of that 2,000 or so documents, it'll choose 50 to retrain the model on, and then report the results using F1 scores. With those 50 documents, we're going to simulate expert labels by utilizing the known labels from the data set, and it's worth calling out that in the real world, you can't assume that the labels solicited by experts are perfect. People make mistakes, so you'd have to use some methods such as inter-annotator agreement to make sure that the labels you're collecting are accurate. For our experiment, we're going to assume that we have perfect labelers. So this is the list of the different active learning strategies we'll be evaluating as part of this experiment. The first is called first N, and this is not an active learning strategy at all, rather just naively choosing the first 50 documents that come in from the pool. So this simulates a strategy where you're not using any discriminating factors and you're just labeling documents as they come in. Top N is going to choose the 50 documents from the pool with the highest model confidence. The way we're handling this and uncertainty sampling in general looks at the confidence score reported by the active learning model as a metric of how well the model knows how to treat that document. So in this case, the top N would be the documents that the model is most sure about that are the top scoring documents. Uniform uncertainty distribution is where we're going to choose document confidences from a uniform distribution across the range. So confidences can be between 0 and 1. We're going to bin those ranges up into 5% bins. So it'd be 0 to 5% is one bin, 5% to 10% is another bin. And then we're going to choose from those bins with a uniform distribution. So we pick a bin, and then you find a document with a confidence score within the range of that bin and solicit a label for that document. Step uncertainty distribution is going to use that same binning strategy, but instead of a uniform distribution, we're going to make documents twice as likely to be chosen when their confidence is greater than 0.5 than when they're less than 0.5. The pyramid uncertainty distribution will choose more documents with uncertainty near the decision boundary at 0.5. So it sort of ramps up from 0 to 0.5 and then ramps back down. Center peak uncertainty distribution is similar, except instead of a linear scale up to 0.5, it's going to be a more extreme ramp up right around the decision boundary. Dynamic bin width is an active learning strategy proposed by Lee and Sethi in the document cited below. So here we're going to sort our documents by their confidence scores and then create 20 bins containing equal numbers of samples. So what this does is it takes into account the if there happens to be more documents with a lower confidence or more documents with a higher confidence, the bins are adjusted to reflect that. And then finally, the last strategy is called adaptive bin distribution. So we're going to start with a uniform distribution of the 5% bins. But when a document's chosen, we're going to evaluate whether the model classified it correctly or not. So if yes, meaning that the confidence was greater than 0.5 and the document was in fact an about document, then we're going to lower the probability from which we choose that bin because our model scored it correctly. If it's incorrect, then we're going to raise the probability that we're going to select that bin because the model got it incorrect, so we need to show more examples like that one. These charts represent the bin distributions I mentioned. So you see uniform, the step distribution, the pyramid, and then the center peak shown here. So let's start looking at our results. For these first two results, we're looking at very large topics, meaning that they had several 100,000 positive examples. The chart on the left actually had over 300,000 of the 800,000 documents in RCV1 were about this topic. So most of the strategies look like they perform fairly similarly, except for the one in pink, which happens to be top 50. So what probably happened here is that the top 50 documents from a pool of 2,000 were likely all very high confidence positive examples of that topic. Because there's 300,000 of these, you can assume that you've got a very high density of positive examples. In fact, it's I think it's around 40%. So the top 50 from that range is likely going to be about. So then when we're retraining our model, we're only showing it one class of documents and no documents from the other class, which will cause model degradation, which is reflected here. In the model on the right, we see a similar degradation for top 50, but we also see that the dynamic bin width and first 50 strategies are also a bit lower as well. So for the model on the right, there was, I think, around 200,000 positive examples. So the class imbalance is a little bit lower. So for first 50, if we assume that those 50 documents are representative of the class imbalance of the whole, then there's fewer positive examples making it in. So that could account for the slight dip there. And we'll address the dynamic bin width on the next slide. Okay, so here we're looking at medium topics. So these are topics with between 20 and 50,000 positive examples in the 800,000 total. We see a large drop in performance for both the first 50 and the dynamic bin width strategies. So we already talked about why the first 50 would suffer. For dynamic bin width, though, we can sort of think about this the same way. If we're talking about 50,000 documents out of 800,000, that's a pretty low class imbalance. So you can assume that the initial confidence scores will skew towards low confidence. So what would happen is that the lower confidence bins, because there's more examples, would become narrower, right? So because they have an equal number of examples in each bin. And then the bins at the high confidence ranges where there are fewer examples would become much wider. So there's more bins for low confidence, there's fewer bins for high confidence, but they're all being selected uniformly. So we end up just selecting more and more negative examples. And again, we'd then be training on mostly one class out of a two-class problem, which can obviously result in model degradation. I think that's what we're seeing here. It's not clear if the author's method had intended there to be a class imbalance of anything other than 50%, but this method does not work well for class imbalances that aren't close to 50%. So on the next slide, we're going to zoom in on a few of the higher performing strategies towards the top of the model. So what you see here is the uniform, the step, the pyramid, the center peak, and the adaptive bin distribution. At first glance, it really seems like they're all performing pretty much similarly to one another. You might be able to pick one or two, like maybe the step function is doing a little bit better, but they're all pretty similar. It's also worth noting that the gray dotted line represents the F1 score of the model if it was trained on all 20,000 training examples. So way more training examples than our models being used with active learning are seeing. And we're starting to see here that the active learning models are actually outperforming that full total. So selectively choosing the right documents is actually helping our model improve better than it would if we just showed it everything. All right, so now we're looking at small topics. So interestingly here, we see a new model sort of take the lead, and that is the top 50. So on large topics, top 50 performed very poorly. But on small topics, it makes sense that it would be doing better. Because in this case, there are so few positive examples. Each of these topics has about 6,000 positives out of the 800,000. So the top 50 would ensure that we're selecting all of those positive examples that come in, whereas any of the probability-based distribution methods might miss a few. So for top 50, we're ensuring that we're seeing all of the positive examples and gaining all of that knowledge while still showing some negative examples. So in summary, active learning works. Performant models with a fraction of the original training data can be created utilizing active learning. Any strategy that selects examples from the full range of confidence values will perform well. It doesn't seem like the distribution that you're choosing them from really matters. What really matters is that you're selecting from that full range. And then finally, the top-end method will work well on topics where there's very sparse positive examples, but it degrades on topics with many positive examples. So you'd probably want some software safeguards put in place to make sure that that doesn't happen. Here's some references, and thank you very much.